Part two. All right, this is part 2 of chapter 19. Now, we ended up last week talking about Gibbs free energy. That was the last thing we mentioned. Now, and we were talking about enthalpy, or not really enthalpy, but entropy as a new concept. And also now we're getting into Gibbs free energy. So what Gibbs free energy is. Now here we're going to talk about, we'll go right here. So we finished off by saying that if you were to figure out the change in entropy of a reaction, it would be the products minus the reactants. And that's the same what we did for enthalpy back all the way in chapter 7, where we would take the enthalpy of formation of the products minus the enthalpy of formation of the reactants, which would equal the enthalpy of formation in the reaction. With entropy, it's the same thing. With Gibbs free energy, it's the same thing. Why is it the same thing? Because they're all related. And the equation we went over last week, which I think because of time or because I just wasn't feeling well or tired, whatever, I didn't really explain it too well, I don't think. But Gibbs free energy equals delta H minus T delta S. So I'll just put T times S for now. All right, so what this means is that Gibbs free energy, I think we mentioned that if it's negative, it means the reaction is spontaneous. If it's positive, it means the reaction is not spontaneous, at least in the forward direction, or in the forward direction. So what this means is that, or what Gibbs is, and the definition that they give for Gibbs, where is it? So it's a state function that is the overall, the way I like to, the definition is not exactly here, but the overall potential energy, hold on, I have to sneeze. Oh, I let that one out. I'm in my apartment, so it's okay. All right. So the overall potential energy that is either gained or lost by the reaction in terms of heat and given, and thank you, Sumi, and entropy. So the net work that a reaction does on the system and the surroundings. So it's the potential energy, and it's really the potential energy that can be converted into work when a reaction goes through and when a reaction happens. And the Gibbs free energy of formation is the potential energy that is given off or gained by the system and the surroundings when the compound that in question is reverted back to its simple standard states. Meaning if you have H2O, the enthalpy of formation, or sorry, the Gibbs free energy of formation would be how much energy and how much work would it require, or would it either require or release if H2O was broken down into its simplified standard states as H2 and O2, which are their diatomic natural states. So it represents all of the work possible by a chemical reaction. That's what Gibbs is. So it's an overarching thing. Now, Gibbs is made up by, like we mentioned, this reaction, delta H, which is the heat of reaction, the enthalpy, which makes sense. We learned about that. Then we're now learning, which is a representation of the system. Then we learned about entropy, which can also be applied to the system, but also takes into account the movement or the net disorder in the molecules in the surroundings that the reaction causes, which is a new thing for us. And it's based on temperature, clearly, because if you have an increase in temperature, the molecules are going to be faster and there's going to be more entropy. And it directly relates to entropy. So we're basically adding these two, even though it's a subtraction sign, we're adding these two factors, or these two factors are factored into the calculation of Gibbs free energy, which can also be found by the products of the Gibbs energy of formation of the products minus the energy of formation of the reactants, just like enthalpy and entropy. But it's an overarching term that involves both of them because it is the overarching work done by a chemical reaction. So any questions on what Gibbs is? And we know this equation will be given on a final exam. So here's an example of some Gibbs free energy of formation numbers. And you don't have to memorize any numbers. They'll all be given when you need them. And for standard state molecules that don't really have any energy associated with them and they form spontaneously, Gibbs is usually 0. Or if it's negative, that means they form more readily than their atomic counterpart. So if you have like a singular hydrogen, or that's not a good example, but some of them form spontaneously. Some of them, if they're 0, that means there's no energy associated with their formation because it's a standard state. If it's positive, that means it requires some work or some external energy to form, as we've known. And negative means that it's spontaneously formed. So if you have carbon and hydrogen just sitting together, it's going to form methane. That's the most stable structure it can form. And you can use those in our reaction here, in our products minus reactants. So Gibbs free energy is a state function, right? So only the products and the reactants matter, the beginning and the end, not what happens in the middle. So here's what the definition is. So free energy is the maximum amount of energy available to do work. Now that work is either broken into, like I said, the heat of the surroundings or the system, and the entropy given to the molecules in the system or the surroundings based on the sign. So here it says, for many exothermic reactions, heat is released due to an enthalpy change, but it goes into increasing the entropy of the surroundings. So it's not available to do work. So that kind of cancels out. But it's the net energy of that reaction that we're talking about. All right, so reversible reactions. So real reactions. Now, in every reaction, if you take thermodynamics, you're going to do examples where assume heat is not lost to the system. And in most cases, or in all cases in real life, most of the heat is lost to the surroundings. So if you have a battery, for example, most of that energy that the battery gives is dissipated as heat. And this is a car battery, but it works for every battery. It works for everything, your phone. So the battery in your phone, the reason why if it works hard, it gets hot. Most of the energy the battery, probably for a phone it's a little bit more efficient, but let's say 30% of the energy that the battery produces. Actually, I would go on a limb. I don't know exactly, but I would say more, because the power required in watts to power the current through the transistors of your phone and capacitors is very little compared to the heat produced. These things are optimized for a very long time. For the last 20, 30 years, they've been optimized. So most of the heat, I would say near most of the heat or work that your phone battery does gives off heat to the environment, to the surroundings. So if you want to think of a new invention, how can we use that heat to filter back into the phone's battery? Maybe make a case that is powered by heat. And then it's a charger case that's powered by heat. I don't know. Don't know if they have that. Don't know, but you guys are engineers mostly, so you can figure that one out. Okay, so then there's delta G naught. G naught, we call it as a standard G, as only means when the reactants or products are in their standard states. And delta G equals that when they're in their standard states, obviously. And we talked about standard states a little bit last time, where we could assume for a gas that the partial pressure of that gas is 1 atm. For concentration, it's 1 molar. And for temperature, 25 degrees Celsius. Under non-standard states, we have this equation. Again, will be given on the exam. And it factors in a factor. Of course it does. There's a factor that is added to the G naught, which is distinctly characteristic of a substance, that relates it to a difference in equilibrium positioning and temperature. So a non-standard state. Now, difference in equilibrium positioning, I mean Q, so the reaction quotient. Now, if Q is 1, that means, well, I mean, that could mean multiple things compared to K. But if Q is 1, that means the concentrations of both reactants and products are about equal. And this whole thing, this whole expression will be 0, and G will be equal to G naught. So we can say that in a standard condition of that, where there's no concentration gradient between reactants and products and no net movement in the reaction, we can say that G naught equals G. So we can also say that knowing there's a big interplay between knowing what G is and then the relationship between Q and K. So I'll get into that now. Well, yeah, we'll do that here, but we'll do a question first about Le Chatelier's, which is our favorite principle, of course. According to Le Chatelier's principle and the dependence of free energy on gaseous reactants and product concentrations, which statement is true? Because it's products over reactants. So that means the reactants are big, products are small number. Results in a more spontaneous reaction than one in which the reactants and products are in their standard states. So when they're in their standard states, that means there's going to be no delta G between products and reactants, right? Because standard states are here. There's going to be mostly 0. They're in their standard states in products and reactants, then there's going to be no delta G is going to be 0. Let's just get that out of the way. So that means if it is a higher concentration of reactants in general, where is, and it says relative, but I mean, in general, where is the reaction to go? There's more reactants and less products. The reaction wants to go to the products. So is that going to be spontaneous? Yes, because it will do that automatically without any external energy given. And the other ones don't make sense. Let's say B, a high concentration of products relative to reactants. So that's the opposite, meaning the reaction has already happened mostly. Results in a more spontaneous reaction than, no, that's not true. It results in a less spontaneous, at least forward reaction. The reverse reaction might be spontaneous. And then C, a reaction in which the reactants are in standard states, but in which no products have formed, has delta G as more positive than delta G naught reaction. That is a tough one to read. So they're all in their standard states. So then that means delta G reaction is the same as delta G naught reaction. And no products have formed yet. So it's the same. They should be the same, not more positive than. Okay. Delta G and K. All right. So at equilibrium, if a reaction is at equilibrium, delta G is 0 because it's not going to happen spontaneously or not spontaneously. It's just not going to happen further at all. We can say that delta G, and if this is, remember the equation from before, where'd it go? This one. If we're saying that G is 0, delta G is 0, we could say G naught equals negative RT natural log of Q, which is the same thing as K if it's at equilibrium. So it's just manipulating the equation we saw before. Now let's look. When K is negative, or sorry, not negative, can't be negative. When K is less than 1, meaning more towards the reactants, delta G is positive, then the reaction is spontaneous in the reverse direction under standard conditions. So delta G is positive. That means going in the forward direction is not favorable. If delta G is negative, going in the forward direction is favorable. But if K is less than 1 at the same time, that means wherever the reaction is, it wants to go towards the reactants because in the forward direction, delta G is positive. So in the reverse direction, delta G would flip signs. And that's also another thing I didn't mention. I kind of assumed it. But if you talk, delta G in a reaction is talking about, in terms of the sign, is talking about the forward reaction. If you want to flip it, the reaction, and go backwards, delta G would flip signs. So let's look at the next case. When K is greater than 1, meaning more products than reactants, delta G is negative. That means the reaction will be spontaneous in the forward direction in order to get to K, right? Because it's definitely favored the products. And delta G is negative, so that's perfect. That means it's going to spontaneously favor the products. If K is equal to 1 and delta G is 0, the reaction is already at equilibrium. Nothing needs to be done. So does that make sense? Any questions on that? I haven't heard anything from you guys yet. No? Okay. We're almost done. All right, let's do this one. So a reaction, remember this weird F, A to B, has an equilibrium constant that is less than 1. What can you conclude about delta G reaction for the reaction? So it's less than 1. That means the reactants are favored, right? Well, good, more reactants. Now, is delta G of the reaction, meaning remember the delta G just means in the forward reaction. Is it going to be spontaneous in the forward direction or not spontaneous in the forward direction? If the reactants are favored. Not so. Okay. The opposite. It would not be spontaneous in the forward direction because K is less than 1. So K is less than 1, meaning its equilibrium likes to lie towards the reactants, meaning in the forward direction, it's not going to be too spontaneous. It's not going to want to go forward, especially when it's at equilibrium. Right? And even when it starts, it's not going to want to go forward that much. So the answer there, the delta G reaction would be greater than 0, would be positive, because in the forward direction, it's not spontaneous. So that's that. If in the reverse reaction, it is spontaneous because K is less than 1. Okay, we'll do one more and then we're basically done. But Christina, do you have a joke? You said you made a funny. Oh, I don't want to put you on the spot, but you wrote it, so I guess you wrote that. Or maybe G is negative. Is that the joke? If so, I don't get it. Oh, you messed up. Oh, well, okay. It's okay. Everybody messes up now and again. All right. Last one. All right. So a reaction is spontaneous under a certain set of conditions. Great. So what does that mean about G? We're not even looking at K. If the reaction is spontaneous, what does that mean about G? Is it positive or negative? Negative. Oh, wait. Christina wrote that beforehand. Whoops. Rivki, that's a really good joke. I like that. What did 0 say to 8? The belt looks good on you. You spelled... Okay. I'll let that slide. You put 1 instead of on. You were in the heat of writing the joke, I understand. Okay, that's a really good one. I like it. All right, anyway, any answers here? So what does G mean if it's spontaneous? What is G if it's spontaneous? Positive or negative? I know it's late. I know we've had a rough day. Negative, good. So if it's negative, then K. If it's spontaneous, meaning in the forward direction, we assume forward direction, is Q less than K or greater than K? Q is less. Less than K. All right, less than K. Reason why: you have delta G, it's negative, so it's spontaneous. Spontaneous in the forward direction. For it to be spontaneous in the forward direction, equilibrium was not achieved yet. So until equilibrium is achieved, what needs to be done? in the forward direction. So Q needs to be less than K. So the reaction needs to go more in the forward direction until Q reaches K.